Hello, my name's Elijah, and today we'll be talking about the handy stand. The handy stand was designed with the college student in mind. It was inspired when I was up late one night working in a common space in my dorm. Because there was such terrible lighting, I couldn't see my calculator to finish my homework. Using what was around me, I managed to prop my phone up into a lamp and began wondering if other students had this problem or if something could be done about it. From this, the team decided to pursue a portable phone stand, something that could be easily packed up and taken anywhere for everyday use. However, as we began to develop the device, we ran into a wide range of customer needs. Some people wanted it to be able to be used in a car. Others wanted to be able to use it for things other than just phones. We determined that college students most wanted a semi-permanent, adjustable stand that they could depend on at home and take with them when they need customer needs. We broke down the handy stand into its essential functions. First, it must be able to hold a phone. Whether this is through a clip or squeeze fit, a snap fit, a magnetic latch, or a suction cup, the phone has to be able to be supported in a orientation that the users can see it and interact with it. The phone has to be adjustable so that it can be turned on its side, it can be used as a lamp, it maintains the variety of positions that the user needs. It has to be able to receive energy, so you have to be able to pass a cord up to it from an outlet. The cord has to be integrated into the device, or there can be a wireless charger integrated into the stand. It must receive user input, whether it's a button, switch, or knob that controls the adjustment of the vertical axis and allows the stand to raise or lower the phone. It must stand upright, meaning that it doesn't need assistance to keep the phone level and above the table or car surface. And it must be able to turn on or off. You have to be able to cut power to the device in case of an emergency. An intellectual property search helped us finalize the features of our first prototype. By looking at what prior art existed, we were able to determine what designs were commonly used in phone stands and which designs we had to avoid in order to prevent patent infringement. One such feature that we were not allowed to implement in our design was a fold-out base, where legs folded out of the base to help keep the phone stand stable. Another thing that we were not allowed to include in our design was a suction cup mount, as it was protected in a car mount that was used in another phone stand. Because of this, we decided to use telescoping tubes, which were not protected in any of the patents that we looked at, and would be able to keep the device very compact. After determining the design, the team conducted a failure modes and effects analysis to minimize the risk in the development process. We first looked at the telescoping tubes because they could lock up due to friction and cause the device to completely fail. However, because this is easily detectable, we gave it a low risk priority and determined that we could fix it by minimizing the number of tubes. Similarly, if the ball and socket joint were to become loose, we would easily be able to detect it, and it could be fixed by using a better material, less susceptible to friction, with good tolerancing. Higher priority concerns were that the mounting device would fail, as this would cause the user's phone to fall down, possibly damaging or breaking it, and giving us a liability. And finally, the stability of the device. For the same reason, the user's phone could fall, but this was a higher risk priority because it was more likely to happen, as the phone was mounted on top of a slender pole and was very heavy, causing it to be unstable. We determined that in order to fix this, we would need to prioritize having a strong, sturdy base with a large area and heavy support to counteract the balance of the phone. The team continued the development process by creating the first model of the handy stand in CAD. This was designed to be a complete model so that it could be used in creating the parts needed for the first prototype. If you look at the image right here, you can see that it includes an Arduino, a breadboard, a base, a motor, and the telescoping tubes and phone stand determined in our model. Additionally, we needed interior components to make the engineering work. Right here, an I-ring was used on the inside of the upper telescoping tube. A fishing line was tied to the inside of the I-ring and run down the shaft to the motor where it was held in tension. The I-ring was secured to the top with a screw, and as the motor rotated, it pulled the fishing line and brought the phone down. Inside each of the shafts, a compression spring was placed so that when the motor wound the other way and released the string, the phone stand was pushed back up. By doing this, we were able to create a working device that took user input to the Arduino and created an adjustable phone stand, exactly as intended. When designing for assembly, we tried to use as many symmetrical components as possible. You can see that each of the telescoping tubes has a 360 radial symmetry, and that again, the compression strings and almost every feature on the device goes in and is very easy to pick up and place. The entire stand has 42 operations to assemble, including 15 screws between securing the telescoping tubes to the base, the motor to the base, the eyelet into the telescoping tube, and various pick-up place procedures. Using design for assembly methods, we determined that these 42 operations would take an estimated 5 minutes and 12 seconds, which led to an assembly cost of $1.30, assuming $15 an hour for unskilled labor plus overhead. After determining the final design for the product and prototype, we created a bill of materials for the prototype. As you can see, the final price was $53.75 for the prototype. However, when designed for mass manufacturing, we could get the price down to $18.70, and when adding the assembly cost, the price point for the product is $20. This is achieved by dropping the price of the wooden base by using a stock component that's made of either plastic or composite material and readily available. We can drop the Arduino and breadboard together into one custom circuit board that can be produced for about $3. The telescoping tubes can go down to 30 cents when they are injection molded. The price goes down over if the injection molds are used over a period of about 3 years. The springs, miscellaneous screws, and miscellaneous electronics all together add up to about $1 when they're bought in bulk. And deals with manufacturing companies for the NEMA stepper motors, the NEMA motor drivers, and the phone clip can bring the price down of each of those components significantly. Through our design, we were able to create a final prototype that met our design specifications and worked correctly. You can see our interchangeable phone mount allows users to take the phone mount off and clip it into a car air vent, which makes it semi-portable exactly as the customer specified. The prototype can be seen right here and adjusts fully when hooked up to power in this manner. The phone stand collapses under tension and raises back up under the compression of springs. We've determined that some key adjustments could greatly improve the usefulness of the handy stand in versions 2 or beyond. First, we could better meet the customer needs by developing 2 separate products. One could be a permanent phone stand that stays on the desk at all times, and instead of using telescoping tubes, uses some sort of rail system that's very rigid and allows the phone to move up and down without any slop or issues with tolerancing. The other product is one that's completely portable. It uses the telescoping method to fold up entirely and removes the adjustability component where